Hi everyone. In this video, we will introduce the definition of the limit of a function of multiple variables, seeking to adapt our definition of the limit of a function from R to R that we previously learned in Math 5610. We will also then look at applying that definition to find the limits of a couple of different functions. So let's begin by just looking directly at the definition. So this is the definition of what it means for the limit as x approaches a of f of x to be equal to L, where both x and L could both potentially be vectors. So let's suppose we have this function f. It is going to map from some set S, which is a subset of Rn, into Rm. And let's let A be an accumulation point of S. So it's an accumulation point of the domain of F. Then we will say that the limit as x approaches A of f of x is equal to L if, for every epsilon greater than 0, there exists a delta greater than 0, such that the norm of f of x minus L is less than epsilon whenever x is in the domain of F, and the norm of x minus a is between 0 and delta. So if we were to pull up the definition from 5610 and put it right beside this, what we would see is that for the most part, these definitions are identical. Now, what things have changed? Well, instead of a bolded x here, we would have a regular x. Why? Because in 5610, we were looking at functions whose inputs were real numbers. Now, this input is a vector in Rn, right? Similarly with outputs, right? Previously, we were looking at functions that output real numbers. Now, this output, L, is potentially a vector in Rm, right? So there's some things that have changed just in terms of the typesetting to denote that some things are now vectors instead of real numbers. So that's one difference. And the other difference is that instead of having absolute values, now we have norms, right? So for a function from R to R, we just had the absolute value of f of x minus L is less than epsilon. And we had the absolute value of x minus a was between 0 and delta. Now, why has this changed? Well, really for the same reasons that we have boldface now. Right now, some of these things are vectors. But fundamentally, the idea remains the same. The idea is I should be able to make my function outputs as close together as I would like. So I would like the distance between my function outputs to be made less than epsilon whenever the difference between my function inputs, the distance between my function inputs is sufficiently small. Right? So all that's really changed is before the distance between f of x and L, when f of x and L were real numbers, that distance could be found by just taking the absolute value. Now this is taking the norm of the difference. That's the metric on Rn. Sorry, well here it's the metric on Rm because we're in the range space. Here, this is the metric on Rn because we're in the domain space. But we're still fundamentally measuring distances. And fundamentally, this definition is exactly the same as we saw in 5610. It says, right, if the limit is going to exist and be equal to L, then I ought to be able to make my function outputs as close as I would like to L. So the norm of f of x minus L can be made less than any epsilon whenever the norm of x minus a is between 0 and some appropriate delta, where again, that delta almost certainly depends on that epsilon, right? Now, if we think about drawing pictures here, it does get a little more difficult because we are working here in multiple dimensions. So the typical picture we drew, if I was just thinking about a function from, say, R to R, right? Sort of what we would often think about is, okay, I have some function, right? And maybe I'm taking the limit at this point A here. And the idea was, well, if the limit is in fact going to be, say, this value over here, L, then for any epsilon you give me, right, I would think about going within epsilon of L, okay? And we would say, well, then for that particular epsilon, right? So each of these little distances here is epsilon. I ought to be able to find some delta so that as long as I'm within delta of A, I make some little delta range around A, and I say, well, as long as I'm within delta of A, it seems like my function outputs, right? All the outputs for my inputs that are within delta of A, all of the outputs are within epsilon of L. Okay. So that was sort of the picture we typically drew for a function from R to R. What would we do now if we're thinking about, say, a function, and because this is one we can more easily visualize, what about just a function from R2 into R? Now, I do this because, right, we can visualize these functions by drawing a plot in R3 where our domain is given here in the xy plane, and then we're thinking about some function f of xy. It's just giving us a real number output, and we plot that output here on the z-axis. So if I think about plotting a function f of xy, so really what I'm doing is I'm plotting, say, z is equal to f of xy, then I'm going to get some sort of surface. So let me just plot sort of maybe a generic surface of some sort here. Maybe it sort of does something like this. Okay, so maybe and try to draw something that's at least a little bit interesting and has some bumps and contours to it, right? So you can sort of imagine I have some function here. And let's say I want to know the limit at some point in my domain. Maybe my point here is this point A. And when I say point here, right, I'm really thinking about a vector. So it has an X and a Y component, right? Okay, so here I could think about, right, going up to, right? So maybe I think that my limit value is this height here, right? So whatever this height is, L, I think that is the limit value, okay? Well, what this definition says is, okay, if I want that to be the limit, then I ought to be able to make f of x as close as I would like to L. I ought to be able to get it to within epsilon of L. So similarly, if I come up here on my z-axis, this is going to give me some little epsilon range around L. So this is like going up to L plus epsilon and down to L minus epsilon. And the only difference here is now it's saying, well, the difference here, because my range space here is just R, which is exactly what it was like in 5610. The difference here is my domain space is R2. So if I look at this, I want to think about what are the values in the domain that are within distance delta of A. Well, since I'm in R2, if I look at all of the points that are within distance delta that I actually get here, and let's use orange here. So that actually gives me a little delta ball. This actually gives me a ball with radius delta, okay? And so what I do is I look at, okay, what happens if I take all the values that are in this little open disk here in the plane and I map them up onto the surface, right? They might look, right? They don't have to be a perfect circle anymore, right? They could be sort of a little wonky, and that's fine. They can be a little wonky, but what I'm really fundamentally looking at is what are the z values I get out when I do that, right? And maybe I see that all those z values lie within epsilon of L. Okay. So it's exactly the same idea. It's just that geometrically what these things look like is slightly different. But these are all still just distances here. Okay. So there hasn't been a huge change in the definition. In fact, we could write one definition that would work for all of these cases, right? You just replace these with metrics, right? And say, well, you use the right metric on your domain and range space. So we could write one definition that would work for both functions from R to R and functions from Rn to Rm. What changes is sort of the geometry of how we visualize and how we think about some of these things. All right. So it's nice to have these conceptual ideas in our head. And as we move through some of this limit stuff, I will provide you with some links to Desmos uh, graphs that will help you visualize and think through some of these things more. But it's also helpful to, for example, just be able to apply this in proving some limit, right? So we want to work through a couple of examples of that as well, just so you can see what that looks like. All right. So the first example we want to look at, we want to start by just looking at a scalar function. So this is going to be a function from R2 into R. Okay. And now we're going to define this, and we'll see why in a second. I'm going to define this as a function from the set of xy in R2 such that x is not equal to y. So this is mapping from a subset of R2 into R. And it's going to be defined by this equation. Now, immediately, just if you look at this expression, you can see why we want that to be the domain. This will be undefined when x is equal to y, right? So we don't want x to be allowed to be equal to y here, or this expression would be undefined. What we want to do is we want to prove that the limit as x comma y goes to 2, 2 of this function is equal to 12. All right, so just as we dealt with other limit problems, one of the things we first want to do is just a little bit of pre-work to sort of think about, what are we trying to do, right? So what do I want to do? I want to show that this limit is equal to 12. So at the end of the day, I want to be able to take, and I should be careful here, right? This is a scalar function, so f of x, y is just some real number. 12 is just a real number. So I just use absolute values here. I want to be able to make this less than epsilon. Okay. So the first thing I'm going to do is I'm actually going to come up here and I'm going to look at this expression. One of the things that I'm going to note is that I can actually, the numerator is a difference of 2 cubes, and it will in fact factor as x minus y times x squared plus xy plus y squared over x minus y. And if I'm in the domain here, right, the domain is when x is not equal to y. So when x is not equal to y, these are zero are non-zero, so I can cancel them. And so this function, right, is simply can be expressed this way when x and y are not equal to each other. Now, notice we're taking a limit as xy approaches a place where x and y are equal to each other. So our function is not defined at this point 2, 2, okay? This equivalence only holds when x and y are not equal to each other. However, if you go ahead and plug 2 and 2 in for x and y respectively, you'll see you do get 12 out. So that's not a proof by any means, but it does make you start to feel like, okay, maybe I'm sort of headed in the right direction. So in terms of expressing this here, though, when x and y are in the domain, this is simply x squared plus xy plus y squared, and then minus 12. I want to be able to make that less than epsilon. Okay. Now, the next thing we have to do is we actually have to do a fair bit of just algebra. And I don't want to spend a whole bunch of video time just stepping through algebraic things. So I've posted a full written out sort of solution here. So you can see all of the algebra and everything. But I actually want to just take that out of the video. And let's just note that we can express this difference here in the following way. This is 6 times x minus 2 plus 6 times y minus 2, sorry, plus x minus 2 squared plus x minus y, or sorry, x minus 2 times y minus 2 plus y minus 2 squared. Okay, so this whole thing, you can do some algebra to rewrite it in this fashion. You want to make that less than epsilon. Okay, now it would work also if you made something that's bigger than this less than epsilon. Okay, and so to make this side a little bit bigger, right, we could just apply the triangle inequality. So we get 6 times x minus 2 plus 6 times y minus 2 plus x minus 2 squared plus x minus 2 times y minus 2 plus y minus 2 squared. If I could get that whole thing less than epsilon, that would work. And now it actually turns out that if I look at these two terms, okay, so I'm going to assume, right, that the difference between xy and 2, right, my goal is eventually to say, okay, that's less than some delta, and if this is less than delta, then this is less than epsilon. That's my goal. Okay, so if I think about this, what this is doing is defining a circle in the plane centered at the point 2, of radius delta. Okay, so in any direction I go, right, the worst this could be is delta. Now, if I think about this just in terms of x minus 2, okay, so if I look at these two things, okay, this, the difference between any particular x value and 2, it certainly can't be more than this distance. So if I look at this distance, right, this distance is just given by this norm here, okay? If I look at any distance, right, the difference between the x values is going to be less than this norm. That's just actually by the triangle inequality, okay? And similarly, right, the y value, if I look at these first two values, so this has an x minus 2, this has a y minus 2. If I look at this x minus 2, certainly, actually, let's just start with an equal to. This is equal to the square root of absolute value of x minus 2 squared, right? And if I add something to it, I'll just make it bigger. Right? But this piece now here, this is just equal to, oops, the norm of xy minus 2, right? That's just the difference between the point xy and the point 2. Okay? So what we have is that this difference has to be less than or equal to the distance between xy and 2. Similarly, we could do exactly the same thing with y minus 2. So I can make each of these a little bit bigger by just replacing them with this norm of xy minus 2. And I'll do another thing here. I'll get the same thing 6 times that. So I've got 6 plus 6 would give me 12. Okay. So I can deal with those two terms, those first two terms in that way. If I assume that my delta, if I go ahead and assume that my delta is less than 2, or sorry, is less than 1, less than or equal to 1, then that will give me, if I look at, say, absolute value of x minus 2 squared, Well, if my delta is less than 1, so I already know that this will be less than or equal to, so this is less than or equal to this. So this squared will be less than or equal to that squared. And if my delta is less than 1, that means this thing is less than 1. And that means that when you square something less than 1, the square is actually the smaller thing. Okay. So if I know that delta is less than 1, and remember, I get to choose delta, so I'm going to make sure it's less than 1. As long as I make sure delta is less than or equal to 1, then x minus 2 squared is less than or equal to this. Similarly for y minus 2 squared. So just to keep track here, these first two terms are less than or equal to this. These two terms, each of these terms will be less than or equal to one of these. So I'll pick up two of those. Okay. And I can go ahead and play almost an identical game here with this. So because if I have x minus 2 and y minus 2, then each of those, the x minus 2 and the y minus 2, will each be less than this. So I'll get that squared. And same argument gives me plus one more of these. So these two go into here. And this term just gives you one more. Okay. So at the end of the day, what all of this is giving me is that I need, so what I have, these are all the same. So I've got 12, 14, 15 of those. So if 15 times x times the norm of xy minus 2, 2 is less than epsilon, if that holds, and I also need to make sure my delta is less than or equal to 1, then I will have that this is true. Okay, so what this tells me, if I divide both sides by 15, is I need this, which should be also like my delta. So I need my delta to be the minimum of epsilon over 15 and 1. Okay, so let's see, we should be able to write that out, right? So we'll just clean things up a bit and write out a formal proof. Blue marker is sometimes a bit harder to erase, so needs a bit of help. All right, so our final proof then, right? And we're just going to let epsilon greater than 0 be given. We're going to choose delta to be the minimum of epsilon over 15 and 1. And then whenever the norm of xy minus 2, 2 is less than delta, we will have that the absolute value of f of xy minus 12. Now, I'm not going to rewrite out all that same calculation, right? But essentially, you'll be able to do that same calculation to get that this is less than or equal to 15 times the norm of xy minus 2, 2. Okay. And because we're assuming we're strictly less than delta, this will be strictly less than well, it'll be 15 times epsilon over 15, which will give me epsilon as desired. Okay. And so it is in fact the case that the limit as xy approaches 2 of this function is 12. Now, I want you to take two things out of this example. The first is that at some fundamental level, there's no difference between these limits and limits of functions from R to R. It's sort of exactly the same overall structure, right? I'm trying for any epsilon, I need to be able to find a delta. So I take an arbitrary epsilon, I work and try to figure out what the right delta is that will depend on that epsilon to make things work. The real difficulty is that because we're in higher dimensions, we have more variables. The algebra is just often a bit more complicated, right? So on the one hand, conceptually, we're just extending the definition in a very natural way. But there's also sort of this practical side of it that it's just a little more difficult because the objects we're working with are just algebraically messier. Okay. All right. I do want to look at one more example. Let's look at the limit of a vector valued function. So that first example we looked at, right, was a scalar valued function. So let's take a look at something that is vector valued. Okay. So let's imagine we have this function now from R2 to R2. If you think back like to when we were first looking at limits, probably the first example maybe you ever did of some function's limit was like a linear function, like y is equal to 3x, right? And in a way, we want to think about what are linear functions from R2 to R2? Well, it's multiply the input vector by a matrix, right? So let's do that. So this function f of xy is just, f of x, if I just think of x as a vector, is a times that vector x. Now, if you prefer, right, you could always represent this. So f of xy, if you want to think about it instead of a vector as just having two scalar inputs, right? So this is just going to be the matrix 2, 1, 1, 2 times a vector whose entries are x, y. And, you can write out exactly what this is. So your first input would be 2x plus y. And then your second would be 2x, x plus 2y. So you can also think of this as a function which takes in two scalar inputs and spits out two scalar outputs. That's equivalent to thinking about a function which takes as a input a vector in R2 and who outputs a vector in R2, right? A vector in R2 is just two scalars, right? Okay. So, but both perfectly good ways to think about it. Both have, utility in different ways at different times. But I don't want to like either way is fine to think about it. Sometimes you'll just find one way more helpful than another. Okay. So, if we want to prove this limit, so this is like my L, right? And this is like my A. Right? These are both vectors. Okay. All right. And so same thing. I need to show that for every epsilon, there exists a delta such that when the norm of x minus a is less than delta, I have the norm of f of x minus L being less than epsilon. Okay. So I'm going to follow sort of the same pattern. Okay. I need to do some pre-work. My goal is to get f of x minus L, its norm, to be less than epsilon. Now, the first step, as before, right, is to just write out, sort of what is this norm, okay? So the first thing we're going to write out, so we're going to take this in this form, and we're going to take, and we're just going to write out what f of x minus L even is. Okay, so if I just, very, very quickly write it out, so it'd be 2x plus y, this is f of x, the first component of f of x minus L, so minus 0. comma, the second component, x plus 2y minus L, so give me a plus 3. So there's f of x minus L. It's going to be helpful, though, to have it written in a slightly different form, and I'll explain why in a second. And in the written work, I've shown all the algebra to do this. You can also express this as 2 times x minus 1 plus y plus 2, comma, x minus 1 plus 2 times y plus 2. Now, you'll notice that what I've done is I've rewritten this so that instead of just having x and y, I have x minus 1 and y plus 2. And the reason I have done that, right, is at some point I'm going to need to deal with x minus a, which is going to be the point xy minus this point here. So what I'm doing is I'm going ahead and introducing factors x minus 1 and y minus negative 2, or y plus 2, just to make my calculation a bit easier. And you can easily check going backwards that these two are equal, that this component is equal to this component is equal to this. I've just done a little bit of algebra to re-express them. Okay, so now I want to understand something about this norm, and I'm going to actually do something first before I worry about making it less than epsilon. Okay, I want to just understand this, and I'm going to make my life even a little bit easier by just going ahead and squaring that. Okay, now why does that make my life easier, right? Well, what is a norm squared, right? So normally the norm is the square root of the difference of the things, but now it's just going to be each component of this squared. So the norm squared is just going to be 2 times x minus 1 plus y plus 2, quantity squared, plus x minus 1 plus 2 times y plus 2, quantity squared, right? So I've got this vector here, right? I want to know what its norm squared is. So its norm would be the square root of each component squared. But if I look at the norm squared, it's just each component squared and added together. Okay. All right. Now, again, if I do a bunch of algebra, okay, basically if I expand these out and collect like terms, I get that this is 5 times x minus 1 squared plus 8 times x minus 1 times y plus 2 plus 5 times y plus 2 squared. Okay, that's just doing the algebra of expanding this out and then collecting like terms. Okay, and now if I look at this, okay, if I look at it, like this term is probably going to be like more or less okay. And the reason I say more or less okay is this is something a term I expect to show up in minus, like in this norm, I expect a term like this to show up. Okay, right? Because what is this? This is by definition the square root of x minus 1 squared plus y plus 2 squared. So I expect a term like this to be showing up here. I expect a term like this to be showing up here. I don't expect this cross term here. Okay. And so I'm going to use a quick inequality here. And I need to be just a little bit. No, okay, I'm good. Sorry, I was worried I had left something out here. So if I want to deal with this cross term here, one way I can do it is I can use an inequality which says that 2 times the absolute value of two things multiplied together is less than or equal to each of those things squared. Okay. This actually comes from, if you subtract this over and then factor it, you get a quadratic. Something squared always has to be greater than or equal to 0. So that's where this inequality comes from. And so what we're going to do is we're going to use it here to bound this. So if I look at this whole thing, this is certainly less than or equal to, I'm just going to take and slap some absolute values on this. So if these are already positive, it stays the same. If they're negative, it makes it larger. Right? Notice we already know these two terms are positive. This middle term we're not sure about. Okay. But we can slap some absolute values on there to make and all we potentially do is make this larger. Okay. So now if I do that, now I'm going to apply this inequality. So if I have 8 here, so really what that's like 4 times 2. And now I look at this. Now this, by this inequality, letting A be absolute value of x minus 1 and B be absolute value of y plus 2, this gives me 5 times, and I can go ahead and slap absolute values on here too, because these are already positive. Okay. And now if I look here, I've got 5x minus 1 squared plus 4x minus 1 squared. So I've got 9x minus 1 squared. And then I've got a 4y plus 2 squared plus 5y plus 2 squared. So I've got a 9y plus 2 squared. And notice that this is really just equal to what? It's 9 times, what is this? X minus 1 squared plus y plus 2 squared. That's this norm squared. Right, so what is all this pre-work done for me? This pre-work has actually shown me that the difference between the outputs squared is less than or equal to some multiple 9 times the distance between the inputs squared. So I've got norm f of x minus L squared is less than or equal to 9 times the norm of, this is really, I can just think of this as like x minus a squared. If I take a square root of both sides, this just gives me that f of x minus L is less than or equal to 3 times norm of x minus a. Okay. Well, and now what I want this whole thing to be less than, so I've now done all the work to show this. I want this to be less than epsilon. I ought to make this less than epsilon over 3. That's going to be my delta. Okay. So now let's just, we ought to be able to sketch out a proof now, right, that shows this. All right, so here's my proof. I'll let epsilon greater than 0 be given. I'm going to choose my delta simply to be epsilon over 3. And then whenever uh, 0 is less than norm of x minus a is less than delta, we have, okay, so we did all that work, right, to show that f of x minus L is less than or equal to 3 times the norm of x minus a. Okay. Now again, if you were writing this as a standalone proof, you'd want to do the work to show this, right? And then you say, okay, now since this is less than or equal to this, and this is less than 3 times delta, and delta is equal to epsilon over 3. And so now I have that f of x minus L in norm is less than epsilon as desired. All right. So what should we take away from all of this? Well, I think one thing to note is that it's still pretty complicated to deal with algebraically. I mean, we can do it, but it's sort of a lot of work. And this was for a fairly straightforward function from R2 to R2, right? In fact, this is a very special, very nice function, right? It's a linear map from R2 to R2. You really can't ask for a nicer kind of function to work with. And already the algebra is a little tedious. So what we will want moving forward, right, we will want some theorems, right, that will help us deal with limits without maybe having to directly prove each piece. For example, maybe I could just say, oh, this is a linear function, it's continuous. So I just evaluate its limit by plugging in. That would be nice. Maybe we can look at limits of functions by looking at paths, right? Well, as you see in the next video, that actually doesn't quite work in the way you would like it to. But we'd like just some additional tools that will help us deal with limits so that we can move on to, for example, things that are defined by the limit, such as derivatives or integrals. So that concludes this video. In the next video, we'll look at limits of functions of several variables restricted to paths in the domain to see what, if anything, those can tell us about the value of the full limit.